Okay, recording has started for those of you that are going to watch the review on YouTube. Okay, I guess let's do a couple reminders first, which I guess I probably had those in the chapter 6 notes at the end, maybe? Where did I put those? Okay, final exam is on May 3rd. That's, is that Tuesday? Let's check. Yeah, that's Tuesday, 1 week from today, at 12:30 p.m. in this room. So Coker 102 is going to be where the final exam is held, and it's going to last for 2.5 hours. The length of the exam is going to be exactly the same as the practice exam. And yeah, here are some reminders about review sessions. Today from 1 to 3 p.m., this one will be on YouTube. There will also be a couple review sessions with Daria from 2 to 4 on April 30th and May 1st. So those days are Saturday and Sunday, respectively, of this coming weekend. Okay, so 2 more 2-hour review sessions. I'm also going to have office hours today from 3:30 to 5 and from 3 to 4:30 on Thursday. So I'm going to do my usual amount of office hours this week. And no office hours next week, obviously, because our exam is going to be on Tuesday before I would normally hold them. But if you want to study in between, then you can always go to the Math Tutoring Center. So the Math Tutoring Center is going to be staffed by the graduate students from 10 a.m. to 3 p.m. Monday through Friday, all through this week and during finals week. So if you want to study on Monday, then you can go to the review, or you can go to the Math Tutoring Center. I think I'll be in there maybe from like 10 to 11 a.m. and then from 2 to 3 or something like that. Maybe I'll put an announcement on Blackboard about the hours that I'll be in the Math Tutoring Center if you want to meet with me specifically. Any administrative questions before we start reviewing? Or does anybody want any just like advice on how to, prepare for the final exam? Okay, here's what I'll say. For those of you that are here in the review session or you're watching the review session on YouTube, I recommend studying the practice exam because the content on the practice exam is going to closely align with the content on the exam. Okay, so with that in mind, we'll open up the floor to any questions that you might have. Does anybody have something that they want to go over? Yeah, Clayton.
Could you go over some annual and continual interest?
Sure. So annual and continuous interest is really just about exponential functions. So why don't we do a quick review of exponential functions? Because after all, there was a question about exponential functions on the practice exam. By the way, has anybody tried the practice exam? Okay, it's on Blackboard and the video solution guide is on YouTube. So I recommend that you try that under exam conditions and then see how you did and see what mistakes you may have made. So the one that was on the practice exam wasn't quite as complicated as annual and continuous interest, but annual and continuous interest will be a good review of exponential functions in general. So let me go back to chapter 3 notes and find the relevant, not chapter 3, I think it's chapter 1. Chapter 1 notes, and we'll review exponential functions. So first we learned linear functions, then we learned cost, revenue, profit, then what did we learn? Supply, demand, and then we learned about exponential functions. Okay, so we had basically 2 possible forms for an exponential function, and the first one was this form where we write p of t is equal to p naught a to the t, where p naught and a are just 2 numbers, right? P naught is representing the original amount, i.e. what you get when you plug in 0 for t, right? If I plug in 0 for t, then anything to the 0 power is just 1. So then 1 times whatever this number is gives us the function output when we plug in 0. So that's why we call p naught the original amount, and then a is the growth or decay factor, right? Okay, so when we learned about interest, we expanded that a little bit. Let's see if I can find the relevant region. Okay, then we learned about natural logs. Where is it? Here we go. Okay, we had two different exponential forms, okay? So one way was to do this p naught a to the t, where a is just any number. And then the other way was any exponential function can also be represented as p naught times e to the kt, right? Just by making this relation, right? We just let e to the k be whatever a is. So in particular, if you want to find out what k is, when you know what a is, all we have to do is take the natural log on both sides, right? And we would get natural log of a is equal to k. So whatever that number is, that's what your k is going to be. Okay, and this is the difference between what we call the annual growth rate being a, annual growth factor being a, which of course the growth rate, when we refer to rate, we're talking about the number r, which a was related to r by the formula a equals 1 plus r, right? So if we had like 5% interest, then our r would be 0.05 and our a would be 1.05. Is this all coming back? Any questions so far? Okay, so then we know that e is just a number. It's something like 2.17 whatever, right? And whatever number a is, say it's 1.05, we can represent that as e to some power, right? So we take 2.718 blah, 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 blah to the something power, and we get 1.05 if that's what a is. Okay, so let's see some examples of annual and continuous interest and maybe just exponential functions in general. Okay, so let's start by swapping a couple of these, right? So we want to write 7 times 1.2 to the t as 7 times e to the something t, right? This is what we want to do. Now, this something is what we call our k, which, by the way, if our a is 1.2, what is r going to be? Just 0.2, right? Because a is equal to 1 plus r. So let's remember that formula. A equals 1 plus r. Okay, and from here, if I want to find out what the number k is, I can do two things. The first way to do it would be to memorize these two statements. We know what a is, right? In our formula, we know what a is. They tell us a is 1.2. So we can find out what k is by simply plugging into this formula. Or not that formula, this formula, right? We just do the natural log of a and we get k, right? Or if you don't memorize this formula, you can easily solve this equation for k. Well, okay, I shouldn't say easily, but we can solve this equation for k, right? How would I do that? Well, the first thing to do would be to divide both sides by 7. Then I have 1.2 to the t is equal to e to the kt, right? And then how would I get the kt down from the exponent? I would do, natural log, right? So ln of 1.2 to the t equals ln of e to the kt, right? Now, using the power rule for logs, I can bring the t down. T ln 1.2 on the left-hand side is equal to kt ln of e. What's ln of e? 1, right? So this is just kt. Okay, now I divide both sides by t, and I'm left with k equals ln of 1.2, which is, let's get our calculator out. We got to go sideways for this one.
0.18.
ln of 1.2. I'm getting 0.079. That seems wrong. I'm doing log of 1.2. I guess that is right. I'm getting 0.07918. Anybody confirm that?
Isn't it ln 1.2, or what do you really work?
I'm doing ln of, oh, I see, that's why. My calculator has an actual log base 10 button, Jesus. Oh, okay, yeah, thank you. You're right, it's 0.18. I was like, that doesn't seem right. You were right after all, it's 0.1823 something. Okay. Okay, so if we wanted to rewrite this in continuous form, it would be P of t equals 7 times e to the 0.18 t, or about 0.18 t, right? Which is equal to 7 times 1.2 to the t, right? If no matter what t value I plug in, if I plug it into this equation or this equation, I'm going to get the same number, right? These two things are equivalent to one another. Okay, so that's how we can transfer back and forth. Let's see some other exponential problems. Maybe we can, let me do one more here from the other section. Let's do one of these, just for fun. Okay, I'm supposed to write an equation for each of the exponential functions whose graphs are shown below. And I'll try to relate this back to what Clayton was asking about. We're going to find two equations for each of these. We're going to find one equation which is in annual form and one equation which is in continuous form. Okay, so let's start with this one on the right-hand side. Okay, we're gonna do this one on the right-hand side. So the first thing that I want to do, okay, is write down the general form of an exponential equation, which of course is P of t equals to what? Someone give me what it is in annual form first. P naught times a to the t. And what would it be if we put it in continuous form? E to the kt, exactly. So our goal here is to find out what is P naught and what is a. If I'm supposed to give the equation, write an equation for each of the exponential functions whose graphs are shown below, what I need to find out are what are the two numbers P naught and a in order to find the equation. Okay, so let's start with this information which we are given on the right-hand side in terms of this graph. How can I write down the information which is captured in this graph in terms of this equation? And let's start with the annual mode, for example. Well, this is the point, what comma what? -2, 9.5. If the point -2, 9.5 is on the graph of the function P of t, are there any relations we can make between the numbers -2 and 9.5? Exactly. What this point being on the graph of this function means is if you take -2 and you plug it in for t, you get 9.5, right? So that's how a function works. We just plug in an input and the function, we evaluate it, and that gives us the output, which is how we determine how tall each point is. So what is that telling us? It's telling me if I do p of -2, then that is what I get when I plug in p naught a to the negative 2 power. And if I do that, I get 9.5. Okay, how about the other point? The other point is 1, 0.5. 1, 0.5. How do I write that down? Someone give me the whole statement in terms of our function.
P parentheses 1 equals P naught A to the 1 equals 0.5.
Very good. Okay, so from here I can forget I ever saw the graph. I just have two equations with two unknowns, and I want to figure out what P naught and A are, right? If I want to figure out what P naught and A are, well, I have two equations, but both equations have P naught and A in them. Is there a way that I can combine these two equations that's gonna eliminate one of those two variables?
Equation on top of the other.
Yeah, I need to take one equation and divide it by the other one. Okay? So, because this is the same thing as 9.5, if I do 9.5 and I divide it by 0.5, I can rewrite, because P naught A to the negative 2 is the same as 9.5, I can replace 9.5 by that number instead. P naught A to the negative 2. And because 0.5 it's equal to P naught A to the 1, I can replace 0.5 by P naught A to the first power. Okay, so what is this telling us? Well, we divide 9.5 by 0.5, and we get 19 is equal to what? What's the magic thing that's going to happen here? Cancels, right? The P naught cancels. So P naught goes away, and we're left with what? A to the negative third power, okay? So, a little bit tricky. You got to remember how to combine those exponents, all right? If you don't remember how to combine exponents, that's all right. Just send me an email. I'll send you some practice for combining exponents, okay? But what we do, if we have a A on the top with a certain power and an A on the bottom with a different power, what we do with the powers is subtract the one in the bottom from the one in the top. Okay, that's how we do powers. Okay, so this is A to the negative 3. So now I want to know, what is A, right? How do I figure out A? Negative third root?
Take the square root.
Square root on both sides? Do we agree? Well, if I take a square root on both sides, that's not going to help us too much because we got a negative third power, right? That would help us if we had a power of 2. Then we could square root, and the square root and the square would cancel each other out, right? All right. How am I gonna get through this one? A to the negative third power equals 19. How do I find out what A is? Natural log. Well, if I natural log, I'm going to put the A inside of the natural log, right? Which I want to get the A by itself, so that's putting it inside of something. So that's going to take us a little further away.
Cube root after you bring down the negative exponent in the denominator.
Yeah, okay, I think we can rewrite this a little bit. We can rewrite this a little bit in the, why don't I maximize this for you all? We can rewrite this a little bit as, this is the same as 1 over A cubed, right? Now is it starting to become a little more clear what we should do? What should we do from here?
Rationalize.
You could do cube root if you wanted to. What would I get if I did the cube root on both sides? I would get cube root of 19 on this side. So cube root of 19 is equal to what? What happens if I do the cube root of 1 over a cubed?
Is that 1/8?
Yeah, you just get 1 over a. Because 1 over a cubed, after all, is the same thing as doing 1 over a times 1 over a times 1 over a, right? So we can do the cube root. Sure. So now we get cube root of 19 is equal to 1 over a. Do I have a yet? No. How do I get it by itself?
I guess bring it back up to the numerator and include a negative exponent.
Like that? Does that tell us what a is?
Multiply both sides by a.
Yeah, there we go. We need to multiply both sides by a. Okay, multiply by a on this side and multiply by a on this side. Then what do I get? I get a times the cube root of 19 is equal to 1. Now what? Now a is equal to 1 divided by the cube root of 19. All right? So that's how I figured out what a is. Okay, maybe a simpler way to do that would have been when you had cube root of 19 is equal to a to the negative 3. Probably what I would have done was cube root of not cube root of 19 yet, sorry, just 19, right? 19 equals a to the negative 3. I would rewrite this 19 equals 1 over a cubed, and I would rewrite this 19a cubed equals 1 by multiplying both sides by a cubed. And then I would divide both sides by 19 and get a cubed equals 1 over 19. And then I would get a is equal to the cube root of 1 over 19, which of course is just 1 over the cube root of 19. Okay, so that's some basic algebra. If you wanted to avoid this entirely, you could have started by, instead of dividing 9.5 by 0.5, you could have done 0.5 divided by 9.5 is equal to a to the 1 divided by a to the negative 2, which is just a cubed. And that would maybe save you a little bit of time. So whichever way you want to do it, there's lots of different ways to do this problem. But we do need to be able to solve these kind of algebraic equations to isolate a single variable here. All right, so am I done with the problem now? No. What is still left to be done?
You have to plug it back into the formula.
Yeah, well, in particular, we know what a is, but we were supposed to find out what is a and what is p naught. Okay, so let's figure out what p naught is now that we know a. How can I do that?
Isolate P naught.
Yeah, I can isolate p naught in one of these equations, right? So maybe I'll start with p of 1. Let me erase this stuff down here real quick. Okay, so I know that p of 1 is p naught times a, and that's equal to 0.5. And I know what a is now. So now I can substitute back p naught times 1 over the cube root of 19 is equal to 0.5. And now I can divide or multiply both sides by the cube root of 19, and I get p naught is 0.5 times the cube root of 19. Okay, so in the end, p of t is going to be equal to p naught, which is 0.5 times the cube root of 19, times what? Now comes a, which is 1 over the cube root of 19, to the power t. And now I'm done. So if you want to multiply this number out and get the decimal, that's fine. You can do that as well. Okay, now how would I switch this into exponential form? Who can help me switch this into exponential form? So So this is p naught times a to the t, right? And now I want to rewrite p naught times e to the kt, right? So the p naught's going to stay the same, right? So I'm going to keep 0.5 times the cube root of 19. And now what I need to do is, instead of writing a to the t, I need to write e to the kt. If I know what a is, how do I get k?
ln of a equals k.
That's right. ln of a is how I get k. So I'm just going to write e to the whatever ln of 1 over the cube root of 19 is, t. And I'm done. So if you wanted to find out what exactly these numbers were exactly, you would just need to do 1 divided by the cube root of 19, plug it into the ln function on your calculator, and that will give you a decimal, which is the decimal which goes here for k. Any questions on this example?
Well, we don't have a cube, or we don't have a e to the x button on our calculator. Can we just leave it unsimplified?
Yes. Yeah, so you can leave in principle, you can leave anything unsimplified as long as your answer is numerically equivalent to the end answer. So if you want to write, for example, 2 to the 4 instead of 16, that's fine. But what I don't want you to do is, if f of x is x to the 4, I don't want you to leave f of 2 as f of 2. I do want you to go ahead and put 2 to the 4. So 2 to the 4 is preferred over function notation, especially when we're doing tangent line approximation. We need to make sure we actually plug into those functions and figure out what we get. But yeah, if you want to leave your answer numerically unsimplified, as in you keep some powers in there, maybe you keep the cube root in there, that's perfectly fine with me. Okay, should we maybe do one more example of these guys? Let me do one more. Okay, let's say I have p of t equals p naught a to the t, and we have 2 points on the function, like 1 and 7, and 3 and comma 28. Okay. I have 2 points on the graph of this function, which is an exponential function. So what I'd like to do is have members from the class start me out and give me each step along the way, so that collaboratively as a class we make it all the way through this problem. My goal is to find p naught and a. So how can I start? Clayton.
Plug in the points that you have to the equation.
Yeah, p of 1 is what I get when I do p naught times a to the 1, and that gives me 7. Likewise, p of 3 is p naught times a cubed, and that gives me 28. Okay, so I hope that my microphone is right. Oh, it is. Okay, good. All right. So what now?
Divide the equations.
Which one goes on top? Does it matter?
Doesn't matter.
Doesn't matter, but which one you wanted to go on top?
28.
Yeah, I like putting 28 on top. Why do I like putting 28 on top instead of 7 on top? Because this way, when I have my equation like this, I'm going to subtract 1 from 3, and I'm going to get a positive power instead of a negative power. So it's just a little simpler that way. Okay, so what do I get in the end here? Simplify the left-hand side, I think I get 4. Simplify the right-hand side, we cancel the p naughts, and we end up with a squared. Which tells me what? A is 2. All right, am I done? No, one thing left to do. What do I still have to do?
Find P naught.
Find P naught. And how do I find P naught?
Plug it back in.
Plug what back in?
The A.
Plug A back into what equation? Okay, the second one. So P naught times A cubed, I know that's equal to 28, and I'm going to put my A in. So P naught times 8, that's what 2 cubed is equal to 28. So what's P naught? Just whatever you get when you do 28 over 8.
3.5.
Which is 3.5. Thank you. 3.5. Okay, so am I done? Yeah, I'm done. I found P naught and A. But if you wanted to rewrite the whole equation, how would it look? P of t equals what?
3.5 times 2 to the t.
Wait, something seems wrong about that. Oh, no, that's right. Yeah, that's right. Okay, cool. Yeah. 3.5 times 2 to the t. All right. So that's how we do these problems where we gotta take 2 points for an exponential function and find out what is the annual form. Now, how do I convert this to exponential form? 3.5 e to the ln of 2 t, which whatever ln of 2 is. You plug it in on your calculator, you get a decimal. Right? So this is by the relations a is equal to, ln of a is equal to k. So if you know a, you can find out what k is by plugging into the natural log function. And how do I get a? A, if I know what k is just going to be e to the k. Okay, and by the way, this equation is just what I get when I do ln on both sides of the other one, right? Okay, so I think that's all I want to say about exponential functions for the exam. Should we move on to a different topic? Or any lingering questions?
Yeah, so Liz, problem number, I think it's 7 on, 1 point, yeah, on section 1.5.
Okay.
Is it slightly different from this general setup?
You said problem 7, right?
Yeah. Like where you have
Oh,
two
okay.
equations and divide both.
Well, really, this is the same. Wait, let's see. Suppose the city is 400,000 years after 1990. If the city's population decreases by 2,500 people per year, find a formula P of t for the city's population t years after 1990. Well, problem 7 is definitely. Oh, 7a and b. I see. It's got 2 parts. Okay. Well, the first part says, okay, if the city's population decreases by 2,500 people per year, should I use P of t equals P naught a to the t? Probably not. Why not?
Because it doesn't have like the decay factor for this.
Right. If you have an exponential function, if you have exponential decay, are you going to decrease your population by the same amount year after year after year? What does the population look like if it goes down the same amount year after year after year after year after year? Looks like a line, right? So this is going to be a linear function. So for this one, I shouldn't use P naught a to the t. I should use m times t plus b, right? And then if the city's population decreases by 6% each year, is that going to be exponential or linear? Exponential, right? And what's my a going to be? What should A be if the population's decreasing by 6%? What does this number 6 have to do with our problem? Sorry?
494, that's what it is.
Yeah, exactly. This is telling us that R is negative 0.06, and therefore A is 1 plus R, which is 1 plus negative 0.06, which means A is going to be 0.94. And what about P naught? Well, P naught is just the original population, right? It says it has population of 400,000 at time t equals 0. So P naught's 400,000, and A is 0.94, so P of t is equal to what? 400,000 times 0.94 to the t. So this problem is different. We don't have to take 2 points. The way you could make a problem which sounds like this, which is a 2-point problem, is you could say the population decreases exponentially. After 1 year, the population is 750,000. After 5 years, the population is 200,000. Right? That would be a 2-point find the exponential function problem. Does that answer your question? Okay, cool. Yeah.
Wait, so when should you use like annual versus continuous?
It'll say in the problem.
Okay.
Yeah, or I'll give you a formula, like, you know, one of the two. Yeah, Gino.
In animals, a continuous is multiplication.
That's right. Yeah, think about it this way: if you took the word continuous but you spelled it with a K, that's how I remember it anyway. As in K-O-N. That's where the K goes. All right. Let's move on to something else. I think that's probably enough focus on chapter 1 for now. Would anybody like to see something from one of the other chapters? Yeah.
Tangent line approximation.
For sure, we can do tangent line approximation. I'd say that's an excellent use of our time. Okay, so, what do you want to do? Tangent line approximation, we can do it with product rule, quotient rule, chain rule. What's your favorite?
Let's do quotient rule.
Quotient rule, tangent line approximation. I love it. Is this the quotient rule, chap? No, this is chain rule. Okay. Why don't we just make up our own problem? That would be more fun, wouldn't it? Okay, find t of x, the tangent line, to f of x at x equals 1 if f of x is equal to x squared minus 3 divided by e to the x. Okay, I've got the whole thing here. So let's do it the same way as we did last time. I'm gonna just let you all kind of take the reins. How should I start a tangent line approximation problem? Yeah.
Take the derivative.
Yeah, we agree. Take the derivative.
Or you can plug in the first point that they give you into the f of x equation.
That's true. Yeah. So you're saying to find f of 1,
Yeah.
right? I think for me, the place I like to start even a little bit before those two things is to write down the equation for the tangent line in a general sense, right? Which we know that the equation of the tangent line to f of x at x equals a is f of a plus f prime of a times x minus a. That's what I like to write down first for the tangent line problems, just so that I remember where it is I'm going. And from here, what I like to do is figure out what a is, right? It's always given in the problem. It'll say at x equals 1, at x equals 4, at x equals 0. That's going to be your a value, right? So we know that this is our a. So I'm going to replace in my formula t of x equals f of a plus f prime of a times x minus a, right? This looks just like the equation of a line. If this was a number, right, and then we add some other number times x, right? That's like a line type of formula, right? So, oh no, I just rewrote the exact same. Holy crap. Oh, my screen is like bugging out. Hang on. Whoa. So my iPad died, so we're gonna continue the rest of the review on the board. So hopefully you can see this somewhat. I'm gonna try to keep an eye on it and make sure that I'm writing on the visible parts of the board. Which of these is better? I guess I like the other one. This one goes away. Okay, so the problem that we were working on was just to find the tangent line to a function. So if the function f of x is given by x squared, what was it, minus 3 divided by e to the x, our goal was to find out what is the tangent line to this function. Oh shit, that is not visible at all. Is it better over there? It is somewhat better over there. Okay. I'm gonna try to work over on the right-hand side. Let's see if that's more visible. Oh, that's nice, man. Thanks. Okay, I think that's as visible as I can make it. So apologies for that. So we want to find the tangent line to this function at x equals to, what did we say? 1? Okay, at x equals to 1. So the first thing was to write out the equation of the tangent line t of x is equal to f of a plus f prime of a times x minus a. And this was, of course, since we're doing this tangent line at x equals 1, this was going to be our a value. So we just put in 1 for a here, plus f prime of 1 times x minus 1. And if we find out what these two numbers are, then this will be the equation of a line, right? Because we would distribute out this number times x minus 1, and we get something times x plus another number, right? Which would be like a y equals mx plus b type of situation, right? So we need to find out what f of 1 and what f prime of 1 are. So it's simple enough to find out what f of 1 is. All we do is we plug in 1, right? F of 1 is as simple as doing 1 squared minus 3 over e to the 1, which is just negative 2 over e. Okay, so that's f of 1. So why don't we just write that down? This is negative 2 over e. And now we need to know what f prime of 1 is. And this is where I think Clayton's comment was coming in. We need to take the derivative of this thing so that we can figure out what that number is, right? So in order to plug in 1 into the derivative to find out what this number is, I need to first calculate what the derivative is. And the way we're going to do that is by using the quotient rule, right? So let me do that over here. If we have f of x, as shown, we just need to find out how to do the derivative of a function like this. And this one is a quotient rule problem because I have one function which I know how to do the derivative of being divided by another function which I know how to do the derivative of, right? And so in this case, I need to use my quotient rule formula. So does anybody remember the mnemonic device we had for quotient rule?
Low D high minus high D low.
Yeah, it was low D high minus high D low, all over low squared, right? That was our key for finding the derivative of a quotient. So what's my low in this case?
So x
It's e to the x. And therefore, what is d low going to be? It's going to be e to the x again, right? Because the derivative of e to the x is just itself. Okay, and then how about for high? High is going to be x squared minus 3, x squared minus 3, and what's d high going to be? Just 2x. So someone help me put it all together. What does it look like when I do it all? I get f prime of x is equal to what?
To the x times 2x
E to the x times 2x
minus x squared
minus x squared
minus 3
minus 3
times e to the x
times e to the x. Like this?
with parentheses.
Yeah, we need parentheses. We're plugging in high, which is x squared minus 3. Always plug with parentheses, right? Okay. In particular, we really need parentheses when our function contains a sum or a difference, right? Because then we need to distribute. Okay, and then how do I finish it up?
And then you square e to the x.
Yeah, I divide all of that by e to the 2x, which is just the same thing as e to the x squared, right? Okay, so now I have f prime of x, so my goal is to find out what f prime of 1 is. So I just plug in 1. F prime of 1 is the number e to the 1, which is just e, times 2 minus 1 minus 3 is negative 2 times e, all divided by e squared. So 2e plus 2e gives us 4e all divided by e squared, which is just 4 over e. You happy with that? Okay, so now what do I need to do? I need to take that number and put it in for f prime of 1. That's my slope. 4 over e times x minus 1. And that's the end of this tangent line business. So, let me recap the steps of doing a tangent line problem. Okay? Provided that you know how to do the derivative of the function. The first step is to write down the formula for the tangent line in general form. The second step is to identify what is your a gonna be. It's always given in the problem. It'll say x equals something. That's your a. You put that number in where you see a in the tangent line formula. Okay, one mistake I see some students make sometimes is they put it in for x. At the end of the day, we're finding a formula for a function. Our function should still depend on x, so we need to leave x alone. But we do want to put in 1 for a. Once we do that, we get an equation like f of 1 plus f prime of 1 times x minus 1. The only thing that's not satisfying about this as an equation is we're like, okay, yeah, but what is f of 1? What is f prime of 1? To find f of 1, you simply plug into the original function. To find f prime of 1, you first find the derivative of the function, and then you plug in 1. Then it's a simple matter of put in the number f of 1 for f of 1, and put in the number for f prime of 1 for f prime of 1, and then we have our equation. Any questions on this one? Okay. Should we do another tangent line, or?
Can we do tangent line of chain rule or tangent line of route of rule?
Sure, we can do tangent line of chain rule or tangent line of some other kind of rule. Why don't we do that? Let's do a tangent line problem where f of x is the function e to the 3x times e to the 5x. All right. All right, so what's the first thing I do when I do a tangent line problem? Write down the equation of the tangent line in general form. Who can tell me what I write?
That is f prime and parentheses x minus a.
Yeah, t of x is f of a plus f prime of a times x minus a. All right. Oh, and we're doing this maybe at, I don't know, x equals 0.
Is this subtracted, not added?
You talking about here?
Yeah.
No, this should be a plus. Okay, so f of a plus f prime of a times x minus a. What's next?
Then you would just, you would go to the, you would find the derivative of that anyway, because when you plug in 0, you just get out 1, right?
Okay, so I think we might be getting a little ahead of ourselves here. Yeah, we plug in our a. What's our a? 0, right? So the first thing I'm gonna do is plug in f of 0 plus f prime of 0 times, I guess, just x, right? Because x minus 0 is just x. All right? So now my goal is to find out what these two numbers are and replace them, right? How do I find out what f of 0 is? It's just e to the 0 times e to the 0, which is what? 0?
It's just 1.
Yeah, it's 1, right? Anything to the 0 power is 1. So this is 1 times 1, which is 1. Okay, so that's f of 0. How about f prime of 0? Find the derivative of f of x first. So if f of x is e to the 5x times, or e to the 3x times e to the 5x, how can I do this derivative? What rules am I going to need?
Chain and product rule.
E to the kx rule. And I'm also hearing product rule. Is there anybody who thinks we don't need the product rule to do this derivative? Yeah, we could also combine them and use e to the kx rule or product or chain rule, right? How could I combine these two? If I take e to the 3x times e to the 5x, what do I get? E to the 8x. Okay, so that's one way to just go straight to the derivative. F prime of x would be just e to the 8x times 8. Okay, but let's see what it would look like if we did the product rule. If we did the product rule, what would we do? We would do the derivative of the first one first, right? So if this is like our f and our g, f times g, then the product rule says we do f prime g plus f g prime, right? Which for us would be e to the 3x times 3 times e to the 5x plus e to the 3x times e to the 5x times 5. Right? And you can see how this is the same thing as e to the 8x times 8, right? If you combine this one, it would be 3e to the 8x plus 5e to the 8x equals 8e to the 8x. Okay, so two different ways that you can do that problem. You don't always have to use the product rule when you see a product if there's a clever way that you can combine stuff. Okay, so now I found out what the derivative of f prime is. So where do I go from here? Plug in 0. What do I get when I plug in 0? 15? I think I get e to the 0 times 8. Right? E to the 0 times 8, which is 8. So in the end, this tangent line formula is given by t of x equals 1 plus 8x. All right, how do we feel about that one? Pretty good. All right, do we want to see any other tangent line examples, or do you feel happy? All right, maybe we should move on to something else. So what else have we not covered? We've covered some stuff from chapter 1 and 2, or really chapter 1, and then we covered tangent line, which was kind of chapter 3, chapter 2 and 3. So do we want to see some stuff from chapters 4 and 5?
Yeah, that would be helpful.
Okay, cool. What do we want to see from chapters 4 and 5?
Global max and min.
Okay, global max and min, that's a good one. Okay, so let's think about this for a second. If we want to do global max and min, first of all, the way global max and min problems are always phrased is in terms of, they say, find the global maximum of this function on this interval. And who can tell me what's the big difference between looking for a local maximum and local minimums and looking for global maximums and global minimums?
Local maximums just impact a certain region, whereas global maxes or mins are like, they fall on like the entire like area of a graph.
Yeah, so we're considering the function over an interval instead of just generally everywhere. But there's another big difference between global maxes and local maxes, which is in terms of where I might find them. Annabelle, you know what I'm talking about?
Global maxes, you have to check the boundaries.
That's exactly right. If we're looking for global maxes, we need to check all the critical points and the boundary points. Okay, so let's see how that works. Let's find the global max and min of, how about f of x equals, x e to the minus x on the interval from 0 to 10. All right. So we have two locations where a global max could occur. Either it's going to happen at a critical point or it's going to happen at the boundary. So what's a good first step for doing a global min-max search?
Find the derivative.
Yeah, find out where those critical points are, right? We should find out where the critical points are. Okay, so first thing to do to find the critical points is to take the derivative and set it equal to 0. How do I do the derivative of something like x e to the minus x?
You have to use the chain rule for that.
I'm gonna need to use the chain rule for the minus x in the power. What else am I gonna need?
Product rule.
Product rule, because I'm multiplying x times e to the minus x. So who can walk me through? What's my derivative gonna be when I do this derivative? My f is my x and my g is my e to the minus x. So I want f prime g plus f g prime. What do I get? Yeah, I get just 1 times e to the minus x plus what? X times what? Negative e to the negative x, right? I pick up that extra minus sign because my k, this is e to the kx, where k is -1. Okay, so I can simplify that a little bit. It's just e to the minus x minus x e to the minus x. Okay, that's the derivative, and I want to know, when is this going to be equal to 0? When's that going to be equal to 0? So I need to solve this equation, right? I need to find the value of x such that if I plug it into e to the minus x minus x times e to the minus x, I get 0. How do I always solve these equations where I set something equal to 0?
This is zero product property. Right?
Yeah, 0 product property, yeah, is going to come into play.
Apply natural log to both sides.
Well, I can't do natural log of 0. So I don't want to do natural log here. There's something a little simpler that I can do. Let's see, what would you do if I gave you an equation like, what would you do if I gave you an equation like 5 minus 5x equals to 0.
Just add 5x to the other side, right? And just divide by 5.
Factor out.
Yeah, you can think about it in a couple ways. You can factor out the 5, right? Or you can move the 5 over to the other side. Let's move this over to the other side. Might as well, right? What do we get? We get well, I'm going to move the x e to the other side. We get e to the minus x equals x e to the minus x. Now what?
Divide the x by the e's.
Yeah, divide both sides by e to the minus x. And I get 1 equals x. Okay, that's one way to do it. Another way to do it would be instead to say I'm going to factor out e to the minus x times 1 minus x is equal to 0, and use, as Brendan said, the zero product property, which says if I have two things multiply and get 0, then one of them was 0. But of course this one's never 0. So that tells me that 1 minus x is equal to 0, and therefore x equals 1. Two different ways of getting to the same answer. So whichever one vibes with you the best, just use that way. Okay, so we found the critical points, because there was just one critical point, right? All right. Now what? I'm trying to find the global max of this function. I know that the global max could happen either at the boundary or at the critical points. I found all the critical points, so what's left to do?
Now
Plug them back into the function.
Yeah, I'm going to take the critical points and the boundary points, and I'm going to plug them into the function and see which number is biggest and smallest. The way I like to do that is to write a table. Okay, you don't have to use a table, though, if you don't want. But I like to say, put a table, and I need to think about what numbers are going to go on the table, right? On the x column, the numbers that I'm going to put are all of my boundary points and critical points. So that's 0, 1, and 10. 0, 1, and 10. And now I need to just take those numbers, and since I'm searching for a global max or a global min, what I want to know is where is the function the highest or the lowest? Which is why when I'm doing this table, I'm going to take those x values and I'm going to plug them into the function itself. Okay, it's a little bit different from some of these other tests that we do where we're either plugging into the first derivative or plugging in the second derivative. We're doing global max search in this table. We're always plugging into our actual function because we want to tell when is the function the highest. Okay, so let's plug in 0. What do we get? 0. Let's plug in 1. We get e. And no, we don't. We get 1 over e, right? When we plug in 1, we get 1 over e. And if I plug in 10, then I get 10 over e to the 10th power. All right, if we just look at these three numbers, which one do we think is the biggest?
0.
I think 1 over e would be bigger than 0. But what about 1 over e versus 10 over e to the 10? What do we think is bigger between those two? Well, if you wanted, you could just use your calculator. But we can also tell, okay, e is a number like 2.7 something. If you take that to the 10th power, you're going to get a really big number. It's like 2.7 times 2.7 times 2.7 times 2.7 times da-da-da, right? That's going to be really big, way, 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 way bigger than 10. Whereas 2.7 is not that much bigger than 1. So this one's the maximum. So 1 over e is where we get our max, and it happens when x is 1. And our minimum is 0. Okay? Because as small as this number might be, it's still positive, which is bigger than 0. Okay? So let me recap the global max search. A global max will happen at the boundary points or at the critical points. So my first step is to find the critical points, and then I make a table where I include all of the critical points that I found and also the two boundary points, 0 and 10 for this problem. And then I just check which which number gives me the biggest height of my function, right? Because after all, that's what the global max is. It's the highest point of the entire function in this subinterval. So I just check all of the points where I could find a maximum, and I check which one's the best. So it's kind of like, you know, I line up all the state champions, and then I compare them against one another to see who's the national champion. Does that make sense? It's kind of that kind of vibe going on. Any questions about the global max search?
You also test your critical point by plugging it back into the function itself.
I did, right? So x equals 1 was our critical point.
Okay.
So then I took 1, and I found out what is f of 1 by plugging in 1 for x in the function. So that was 1 times e to the minus 1, which is how I got 1 over e. Is that what you're asking about?
Yeah, but if you're trying to find a local maximum, you would plug it back into the first derivative.
Right. So yeah, exactly. So we determined that this is the global max of the function, right? But we didn't say whether or not it's a local max or not, right? I mean, it is going to be a local max, but the way that you would need to prove that it is a local max is using either the first or the second derivative test. But it's sort of irrelevant because we're just comparing all of the places where you could have a local max or a local min, and we figure out which one's the biggest between all the local maxes and local mins. Because our collection contains all the critical points where there could be a local max or min, we end up getting the global max. Okay, any other questions on global min-max? Okay, let's see how much time we got left. What time is it? Also, this thing is sort of working again. At least it's allowing me to power it off. So I'll power it off and we'll see what happens when it comes back on. Keep an eye on that. All right, what should we talk about next?
Can we do some of section 6?
Sum of section 6. Sure.
Like when you would use, like when you would add c into the integral, and when you would just, and when you wouldn't.
Okay. Sure. So the question is, when would we add c to an integral, and when are we gonna not add c to an integral? Can anybody answer it right away?
When it's definite, you don't. When it's indefinite, you do it.
Exactly. When it's a definite versus an indefinite integral. Okay, so let's talk about the difference. A definite integral is integral from a to b of f of x dx. And what we get when we do this is the area under f of x from a to b, which also is equal to capital F of b minus capital F of a, provided that capital F prime of x equals little f prime of x. Equals little f of x, sorry. Okay, so these are the three, these are basically the fundamental theorem of calculus. What does it say? It says, if I integrate under a curve, I accumulate change. I get the total area under that curve from a to b. And the fundamental theorem of calculus is this equality here, which says that this integral is going to be equal to capital F of b minus capital F of a as long as capital F is an antiderivative of little f. So at the end of the day, if I take some number and I plug it into a function, and I take another number and I plug it into the same function, and I take those two numbers and I subtract them, I'm gonna get a number, right? So let's talk about the difference between the definite integral and the indefinite integral. Okay, well the indefinite, in is a prefix which means not, right? So the indefinite integral means not definite, which means that we don't have a definite interval over which we are going to do this integral. We're just going to write an integral sign, but we're not going to write any numbers here and here. We're just going to put the function in here. Okay, and the indefinite integral is defined to be the collection of all antiderivatives of little f of x, i.e. capital F of x plus c, where capital F of x is any antiderivative. Okay, so this is the difference between a definite and an indefinite integral. A definite integral, we have bounds, goes from a to b. When we do a definite integral, we always get a number. When we do an indefinite integral, we don't have bounds. In means not, so not definite integral means we don't have bounds. And what we refer to when we talk about integral of f of x dx with no bounds is we don't have the fundamental theorem of calculus to say plug in this one then minus this one. So we need to come up with what we're going to take this to mean. And by convention, we just choose to say, okay, when I write this integral with no bounds, I'm just going to be talking about the collection of all the antiderivatives of f, which if I have an antiderivative of little f, I can get another antiderivative by adding a constant, right? Because if I do the derivative of this, of f of x plus c, I'll get the same thing as if I just did the derivative of f of x, right? Or f of x plus 9, or f of x plus a billion. I do the derivative, the constant goes away, right? So I just take any old antiderivative and I write plus c to denote that I could add any number to that I wanted. And this defines a collection of functions. It's all of the functions that I put in my bucket are, first of all, the function f of x, and then that function also plus any other number, are all the functions which go in my bucket, right? So this is like a set of functions. If you remember way back when we were talking about set theory. Okay, so does that answer your question about the difference between a definite and indefinite integral?
So problems ask for like the integral and they don't really mention anything about any bounds, then is it safe to assume that it's an indefinite integral?
Not quite. So, for example, someone could ask a question like someone could ask a question like the one on the practice exam, which says v of t is the velocity at time t, and they could say, write an integral which expresses the distance traveled after 2 hours, and assume that v is in miles per hour and t is in hours. This would be an example of a problem that's asking something about integration in a kind of a roundabout way, right? What's the relationship between the velocity function and the distance function?
The distance is the derivative of the velocity function.
Distance is derivative of velocity. Do we agree?
Velocity is the derivative of the distance.
It's the other way around, right? Velocity is the derivative of the distance. It's the rate at which the distance is changing, right? My distance from the desk is changing as I walk forward. How fast I'm going is my velocity, right? So that's the rate at which my distance is changing, right? So how do I have a relationship between v and d involving an integral? So if I was going to apply the fundamental theorem of calculus, right, to two functions, one of whom is the derivative of the other, what would the fundamental theorem of calculus say? What does the fundamental theorem of calculus say, period? Forget about v and d.
That capital F of b minus capital F of a is equal to the integral of that function.
This is what the fundamental theorem of calculus says, right? Where little f is the derivative of big F. So what role is d and v playing in this kind of an equation? Which, by the way, we should go from a to b, right?
So b of 2b capital F, whereas or while d or t would be little f.
Sorry, so which one's capital F?
B of t.
V?
Yeah.
We agree?
Or is it the other way around?
The other way around, right? Because what is the relationship here? We want capital F prime of x equals little f of x. If we're going to put v in for f, then we should have the relationship that v prime of t equals d of t, right? Which says the derivative of the velocity is the distance, right? And that's not quite right. We know it's the other way around, right? It's the derivative of d is v. So how can I rewrite this statement in terms of d and v? Well, everywhere I see a capital F, I'm going to put a little d. And everywhere I see a little f, I'm going to put a v. Right? So if I was going to rewrite this, it would be d of b minus d of a equals integral from a to b of v of t dt. Okay? So, maybe these people can't see that. So this is the relationship between the fundamental theorem of calculus where I'm just, since these two functions share this relationship, any two functions that share a relationship like that, I can plug them in to the formula. I just need to keep the roles straight throughout. Okay, so how would I write this integral which expresses the distance traveled? Well, if I take this, d of b minus d of a, what is that expressing in terms of the problem? It's distance from a location at time b minus distance from a location at time a. How do I express this in terms of the problem?
D of b is 2 hours and d of a is 0.
Right, so you're on the right track, but in terms of the problem, the way that I can describe this number, right, whatever this number is, it describes precisely the distance traveled from time t equals a to time t equals b, right? That's what this describes. D of b minus d of a is the difference in distance from time b to time a to time b, right? And that's what I'm supposed to describe. I'm supposed to use an integral to express the distance traveled for the first 2 hours of the trip. So what's missing How do I finish this off?
Put 2 and 0 into.
Yeah, put 2 and 0 in for b and a, right? So I know that d of 2 minus d of 0 is equal to the integral from 0 to 2 of b of t dt. So what is this number? This number is the distance traveled over the first 2 hours. And I say that the distance traveled over the first 2 hours is equal to the integral from 0 to 2 of b of t dt. That's what I'm looking for, right? That's what the problem is asking for. You see what I mean? So you can do this with anything, right? Any two functions which share a derivative relationship like this. For example, you could have the rate of snowfall, right, would be the derivative of the amount of snowfall. Or you could say the rate at which the drug is leaving the body is the derivative of the amount of that drug which has left the body. And then you just make sure that you keep these, you think of these roles as fulfilling this kind of relationship. As long as you remember the fundamental theorem of calculus here, any two functions which share a relationship such that the derivative of one is the other, you can formulate in terms of the fundamental theorem of calculus, which loosely speaking says the accumulated velocity over time is equal to the total distance traveled during that time period, right? Or if we accumulate the disintegration of a drug over a time period, then what do we get? The total difference in the amount of that drug which is in the body, or so on and so forth. Is that helping to solidify this idea of the fundamental theorem of calculus? Okay, so let's do another one of those. What if I rewrote this as what if I wrote d prime of t is the rate at which a drug leaves the body, and d is measured in milligrams per hour. Milligrams per hour. Let's say t is measured in hours. Let's write an integral which expresses the total amount which left the body of drug, total amount of drug which left the body during the first 30 minutes. Anyone want to take a crack at this one? So we have a function which is measuring a rate of change of a substance. And I have a question which is asking about the total change of that substance over a time period. Gino, you want to try?
Yeah, wouldn't it just be d1 1/2 subtracted by d0 equals the integral of 0 1 1/2 dt?
Integral of what, sorry?
0 to 1 1/2.
0 to 1/2, right? 0 to 1/2 of what?
dt.
Close. We're going to put, if this is d, if this is a relation, this is a statement about d, right? So I'm talking about like a function here, right? Like capital F. What relationship do we have between the function capital F and little f? Yeah, little f is the derivative of capital F, right? So if I write d here, what should go here? D prime. Okay, so what does this say? What does d of 1/2 measure? This is amount of drug in the body after a half an hour, minus the amount of drug which is in the body at time 0, right? So this left-hand side tells us the difference between the amount of drug after a half hour and the amount of drug when we started. And we say by the fundamental theorem of calculus, that's equal to the integration of this rate of change, okay? Where of course we're gonna integrate from 0 to a half. Why a half and not 30? Yeah, because t is measured in hours, and I'm supposed to do this for the first 30 minutes. If t is measured in hours, then t should go from 0 to 1/2, right?
130 to 60.
30 to 60.
Yeah, because isn't that another way of expressing like 0 to 1/2?
I think 0 to 1/2 would be like 0 to 30 if you're talking about minutes. But in this particular case, we're talking about the first 30 minutes. So we should definitely start at time 0, right? And then how we choose what the upper bound is going to be depends on what t is measured in. T is measured in hours. So the way I describe the first 30 minutes in terms of hours is I go from 0 hours to half an hour. That's the first 30 minutes. Does that make sense? Okay, so you can do this with any such function that you want, as long as you have a rate of change, you integrate the rate of change, you get the total change. Okay, the only tricky business is sometimes they'll give you this in terms of, they'll give you like minutes when the units are hours, or they'll give you hours when the units are minutes, or something like that. Okay. Should we move on to a different topic, or we want to see another example of that? Okay, one more example of that. Let's say that g of z is capital G prime of z. And our question is, if this is a graph of g of z, this is a graph of g of z, and this is of course z equals 0 here, and then here is maybe z equals 5. The question is, if this length is a, describe the length a as an integral. Involving g of z. All right, getting complicated with it. Okay, so what do we have? We have a, which is describing what? A difference in height of what function? It's describing the difference in height of capital G, right? So how could I write let's forget about writing the length a as an integral for a second and ask ourselves, how could I write the length a in terms of capital G? sorry, capital G what?
B.
Of, I'm gonna do 5 because
Oh, yeah, five.
we're at 5. Capital G of 5 minus capital G of 0. You agree with me that G of 0 is this height here, right? That's G of 0. And G of 5 is this height here, right? This is G of 5, right? I just get the height of G by plugging 5 into the G function, and I get this height. So I want to find an expression which expresses G of 5 minus G of 0, where capital G is my function. What am I looking for here? Okay, I want integral of what? From what to what, first of all? 0 to 5, that's clear. And what goes in the, what am I going to integrate?
G prime, G
prime.
Okay, I'm hearing a lot of things. So one person at a time. So I'll raise your hand. What, Gino?
G prime Z with lowercase g.
G prime of z with a lowercase g. dz. Do we all agree with that?
Wouldn't it be capital G prime instead?
Yeah. First of all, it should be capital G prime. But what is capital G prime? It's little g, right? So let's go back and look at this fundamental theorem of calculus. What does it say? Capital F is integral of little f. So we went one too many derivatives. So we should do just little g here of z, dz. Okay, what if they told you capital G of z is x squared minus 3? What would I do differently? The only thing I would do differently is here where it says G of z, I'd put, not x squared, z squared minus 3, right? The only difference is I put z squared minus 3 here. Okay, so sometimes I'll give it to you like that. Give you a function. All right, so that's writing integrals to express a total change. Any other questions about that? All right, then we can talk about something else. So what's the next topic gonna be, do you think? Or do you want, what do you want to do?
Can we do half-lives?
Half-lives, sure. So let's do a combination problem. Okay, we have, let's say, a radioactive substance. Is decaying. When the experiment started, physicists had 1 kilogram of the substance. Okay, radioactive substance is decaying exponentially is sort of implied, but I'll write exponentially. Physicists had 1 kilogram of this substance when we started the experiment. After, I don't know, after 7 years, there is still 0.9 kilograms left. After 7 years, there's still 0.9 kilograms left. How long until there is, or why don't we just say, what is the half-life of the substance? Okay, so we were doing this problem. It's kind of hard to see, but it's a radioactive substance. It's decaying exponentially. When the experiment started, physicists had 1 kilogram, and after 7 years, there's 0.9 kilograms left. We're supposed to find out how long is it going to take for half of it to be gone. Okay, so I think we should start with the exponential equation, right? Which is going to express how much we have left. So let's say P of t is how much we have left after t years. What should my formula be? Well, I could use whichever one I want. I like P naught a to the t because it's a little less fussy. And I think most of my students don't like doing e to the kt as much. So that's what I like to do. So we'll do P of t equals P naught a to the t. Now let's try to take the information which is given to us in terms of the problem and write it down in terms of mathematics about this equation. Who wants to start me off? Anything that I can write down about my equation P naught a to the t?
7 equals t.
Yeah, okay, let's start with this sentence here. When the experiment started, physicists had 1 kilogram. How can we write that down in terms of this equation?
So 1 equals P naught.
Yeah, 1 equals P naught. Or okay, if we're talking about when the experiment started, what is t when the experiment starts? 0, right? So if I plug in 0 for t here, what do I get? I get P naught a to the 0 equals 1. That's what this sentence says. When the experiment started, physicists had 1 kilogram. That tells me if I plug in 0 for t, I get 1. If I plug in 0 here and I do a to the 0, I get 1. So this tells me that P naught is equal to 1, which makes sense. P naught is the amount that I start with. Okay, now I just need to figure out what A is, and then I'll be like most of the way there. Now it says after 7 years, there's still 0.9 kilograms left. What does that tell me? How can I write that down mathematically?
Maybe 1 minus 0.9 for A.
1 minus 0.9 for A.
Or maybe
Okay, but in terms of this sentence here, right? What is it saying? It's saying after 7 years. After 7 years, what is t gonna be?
So 8 to the 7 equals 0.9.
Yeah, it's gonna be. We can first of all we can rewrite this equation as we know what P naught is now, right? It's just 1. So this is just a to the t, right? So what this is telling me is that if I plug in 7 into the equation, then the output is 0.9. So if I do P of 7, that gives me a to the 7, so this is telling me a to the 7 equals 0.9. So how do I figure out what a is? I got a to the 7 equals 0.9.
take the 7 through.
Take the 7 through, or the 1/7 power if you want. 0.9 to the 1/7 power. That's how I would do it on my calculator, because my calculator doesn't have a 7th root button. So I would do 0.9 to the 1/7 power, which is the same thing as a 7th root. Okay, so someone tell me what that number is, roughly.
0.95.
Sorry,
985.
Okay, so 0.985 is our A. So now we have the whole formula, P of t equals 0.985 to the t. 0.985 to the t. So, how do I answer the question? what is the half-life of this substance? I've done all this work to find the formula for how much is left. Yeah.
Set it equal to 0.5.
Yeah, I want to find the time t such that if I plug it into the equation, there's exactly half a kilogram left, right? Because I start with 1 kilogram. So I want to make sure that I want to find the time t such that this is equal to 0.5. So I need to solve 0.985 t equals 0.5. That's a tricky one because what we need to solve for is inside of an exponent, right? So what tools do we have for getting things out of exponents? Log. So we're going to take the natural log on both sides. You get ln of 0.985 to the t equals not 0.5, equals natural log of 1/2. Okay, how does that help me? Yeah, now I can bring the t down. So I get t times ln of 0.985 equals ln of 0.5. And now what?
Just divide by ln of 0.985.
Yeah, I'm going to divide both sides by whatever that number is. So I get t equals ln of 1/2 over ln of 0.985. And I'm done. All right, so this is how we do half-life problems. And in fact, this was a half-life problem where at the start, it was actually sort of preceded by a give you 2 points, find the exponential problem, right? Find the exponential function. The 2 points which were given were 0, 1, and 7.9, right? I could have just said find the equation of an exponential function which passes through these 2 points. Then find t such that p of t equals 1/2. P naught, which p naught was 1, right? Okay, so was that Eli who was asking about that? Do we feel better about half-life problems? What would I change about this if it was a doubling time problem?
You do times 2.
Yeah, I would do times 2, right? So when I wanted to plug in a half here, right? That was what I'm supposed to get after a certain amount of time t. I would put 2 times whatever my initial amount is there, right? That's the only difference for a doubling time. Or for a quartering time or whatever, right? Okay. What time is it? We got 10 minutes left. We can do something else, yeah?
Wait, so if it was doubling time, it would just be equal to 2 instead of 0.5?
Yeah, exactly. Yeah. Because if we start with 1 kilogram, if we're doing a doubling time problem, we want to know how long until we have 2 kilograms, right? Or if we started with 10 kilograms, what would I put here? For a doubling time, 20, right? Yeah. Okay. So let's talk about a couple other things. The last things I want to talk about for the review are how to do definite integrals. Okay. How to do definite integrals. So let's do one. Let's find the area under f of x equals x squared plus 2 from why don't I say over the interval 0, 3. Okay, so we want to find the area under this curve from 0 to 3. So let's do a picture of what this looks like. So x squared plus 2, what kind of function is that? It's a parabola opening up, and what about the plus 2? How's that going to switch us? It's going to move us up 2, right? So we have a parabola which starts at 2, and it opens up like this, right? And the area we're supposed to find is from 0 to 3. So we count 0, 1, 2, 3, and we put a dashed line here, and we're after that area which is shaded here, right? Okay, so someone maybe start me off. What is going to be relevant for finding the area under a curve?
Height.
The height of the curve, for sure, is going to be relevant. In terms of material from the class, did we learn any ways about finding how to figure out area under curve? Riemann sums, or what were Riemann sums about doing? Riemann sums were in order to approximate the total area, which is given by the integral. So this is a problem about integrals. We're supposed to find this area exactly, so no Riemann sum approximations. We need to actually figure out what this area is. Okay, so how am I going to do this integral from 0 to 3 of x squared plus 2 dx? That's what this is. This integral, like we said, the definite integral represents the area under the curve from the first bound to the second bound, which is this picture exactly. And we had some special knowledge. We learned about the relationship between an integral like this and something else. Someone help me out.
Capital S.
Yeah, the antiderivative, right? We learned about the relationship between the area under the derivative and the difference in height of the antiderivative. So how am I going to figure out what this number is?
Take the antiderivative
Yeah, take the antiderivative, and then what?
and then plug in the bounds.
Yeah, and then plug in the bounds. Okay, so I need a function whose derivative is x squared plus 2 dx. So how am I going to find an antiderivative for this function?
Use some rules.
I'm going to use the rules for finding antiderivatives, which we learned. So the first two that we learned were how to find the antiderivative of a constant, and the second one was how to find the antiderivative of x to the n, right? Which seem like the most pertinent rules for this problem, right? So how do I find the antiderivative of something like x squared?
N plus 1 over N plus 1.
Yeah, I raise the power by 1 and I divide by the new power, right? So it's gonna be x cubed over 3. How about 2? What's gonna happen to 2? Plus 2x. And plus c, right?
No,
No. Why not plus c?
because there's
Because this is a
definite.
definite integral. And a definite integral, we definitely do not need c. I just made that up. Okay, so anything missing still?
Yes.
Yes, I need this guy, which tells me that I still need to plug in 0 and 3, right? Okay, who can explain for the class what this symbol means? Gino.
I don't know how to put it in words, but just squiggly line thing, 0 and 3. Just like, oh, the area between 0 and 3. Or the area under it.
It's a little more simple than this. This is some instructions, right, for what I need to do with this function, right? This integral from 0 to 3 says find the area under this curve, right? Or find the antiderivative and then do something, which is characterized by what this notation means. What this notation means, okay, if I write f of x and then I write a bar, a and b, this is defined to be what you get when you plug in b and then subtract and plug in a. Okay? That is what this says. Okay? So if you write a bar like that to the right of a function with two numbers, it says plug in the top number, then do a minus sign, then plug in the bottom number. That is what that notation means. So how do I make that work with this guy? What should I write next?
You should write 3 cubed over 3.
3 cubed over 3
Plus 2 times 3.
plus 2 times 3 minus
parentheses 0.
0 cubed over 3
And then
plus 2 times 0. Right? Okay. So that's what this notation means. It says first plug in 3, then do a minus sign, then plug in 0. All right. So that's how we find the area under this curve from 0 to 3. It's about finding the antiderivative. Okay, now let's do another one. Let's say r of t equals e to the 3t minus 1 over t is the rate at which, I don't know, the rate at which what happens? Someone give me an example of something happening that we can measure the rate of.
rain falling.
Rain falling, the rate at which rain is falling. In, I don't know, inches per hour. Yeah, we're gonna use dumb American units. All right, inches per hour of rainfall. Now we're gonna ask a question. The question is, what is the total rainfall in the first 3 hours? All right, is this a problem about integration? Yes. Why do we think this is a problem about integration? What's signaling us to what's the cues in the problem that are making us think, this is something about integration? I'm talking about a rate of change, and then we're making a jump to say something about the total change, right? The total change, right? Okay, so how can I write down what this total rainfall is in terms of an integral?
0 to 3 of integral and then the equation RT.
Yeah, if I integrate the rate at which the rain is falling from 0 to 3, I'm going to get the total rainfall for hours 0, 1, 2, and 3, right? Or 0, 1, and 2. Or 1, 2, and 3, however you want to call them. So e to the 3t goes here, minus 1 over t dt. So now I need to figure out what this number is. How do I figure out what it is? Someone help me out. Take the antiderivative of this function. What's the antiderivative of e to the 3t?
E to the 3t over 3.
E to the 3t over 3, right? So it's kind of like the reverse of the e to the kx rule for derivatives. When I'm doing antiderivatives, rather than multiplying by that number, I divide by it. And then minus, very good, ln of absolute value of t. Missing anything? Yeah, I need this line and 0 and 3. What does this line with 0 and 3 mean?
The difference between those two.
Difference between when I plug in 3 and 0, right? So which one do I plug in first? 3 comes first. So I get e to the 9 over 3 minus ln of 3. And I subtract from that, I shouldn't have done 0. I should have done 1 to 3, sorry. Minus e to the 1, so not first 3 hours, but during the 1 to 3 hour range. E to the 1 over, or not 1, 3 over 3 minus ln of 1. which is 0. So whatever we get when we take this number and we subtract this number from it, that is going to be the total rainfall during those hours. Okay, so integrate a rate of change, we get the total change. Any final questions on this one? Okay, then we'll close for today. So don't forget there's some more review sessions coming up. I also have office hours today from 3:30 to 5 if you want to go do some more stuff on Microsoft Teams, although I don't know, I might have to cancel those because my iPad's not working. All right, well, I'll figure it out and I'll send an email.